Previously, when I was describing what we have installed, I was showing this plot here, this graph, the installation where we have similar positions where we are running experiments. So from today onwards, I'm going to show this figure now. It's it's better and proper. Yeah. So as you can see, there is one thing. Yes. Okay. One thing that is wait. Okay. So perfect. The external monitor was jumping around. So there is one thing that we have to
Yeah.
What?
You have to.
Yeah, I have to restart the sharing.
Yeah. Now
it's done.
Yeah.
Sorry. What type? So now I'm showing, as I said, this photo here from today onwards, because we have now running installation here. Hopefully, it will run for a very long time. So I'm really happy that we did it. So, but anyway, there is one final thing that we have to discuss, and that is because when we do ice and when we do post-processing, we are getting a lot of time domain data. What I mean about that is, so we have our testing bed here. For example, this is now in Dajon, and we have the control PC also located near. So this control PC controls the whole experiment and does the data acquisition. And when it does this, every so often, it generates a couple of 6 to 10 files, depending on how many excitation units, how many excitation signals we get. And these files contain time domain data of the excitation unit plus the output of the fuel cell. So in essence, there are 21 channels of data sampled by 20 kilohertz for, let's say, 150 seconds plus. And all of this can generate quite a lot of data. Currently, I think from what we saw, we are around, I would say, 25 megabytes per one ice. This doesn't mean that the ice curve is 25 megabytes. 25 megabytes are the data that we are going to use to calculate one ice curve. The ice curve will have really, I don't know, 200 points, so it will be really, really efficient. But this means that over time, these files will start to pile up on a PC, and it is firstly it is unsecure to have everything in the same location. I mean, the PC can fail or whatever. And secondly, it is the question of capacity. So that's why we are transferring this to a cloud storage device. Thank you. To a cloud storage device. We have it at my instance. Doesn't matter it doesn't need to be there. It can be anywhere where you store it. But we provide this infrastructure. We tried this. So this, what you see here, has been tried here in Dajon. We did one such a setup yesterday, and today, without any interference from my side, the guys in the laboratory managed to do all of this. So they start up the stack, made a data acquisition, generated 6 files, upload them to my Slovenian cloud. This is not a key point in the process. This is how we can exchange data on the long run. No one has to do it. You can do everything locally. But this is the pipe. So on top of it, what we do when we do online these long-term experiments, we have a system that logs a lot of processing data, like mass flows, temperatures, voltages, currents and everything. But you here in Daejeon laboratory, you have everything this done locally, so you don't have to think about this. This is something that you already have, and it's covered. At some of our partners in Europe, they don't have such infrastructure, so we have some such things to remote those experiments remotely. This is not of your concern at the moment. So just to, I'm telling this because there are places, strangely enough, where they don't have capabilities to monitor the experiments in real time. So just to give an idea, this is a snapshot from yesterday, as you can see 12 hours ago, of the data that is generated through several ongoing remote sensing projects that we have. This is one European project that is ongoing for the last 4 years. So currently there are ice curves and time domain data of 3 terabytes. So this is just piling up. People are analyzing it. This contains data from France and Switzerland. So this morning we did one more drop point H together, and we uploaded the first data here. This does, as I said already, this is not a mandatory part of the processing, but this is an easy way to exchange data. Anyway, so I'm not going to waste your time. What we have and where. There is one thing that I would like to show you. This is a real snapshot. So like a couple of hours ago, we have a running battery pack of 300 batteries, lithium. We are testing long-term behavior of this battery pack. So we are every 24 hours, a set of 10 batteries undergoes an ice curve. So we practically measure ice curves on 300 batteries over and over. So every 30 days, every battery is cycled with at least one ice measurement. It has exactly the same setup like you have here in Daejeon, except these are low power batteries and there are 300 of them. But these kind of experiments we are running in parallel all the time. Okay, so how a simple processing pipeline goes from a software perspective side. So we have an experiment and we have a data acquisition system. So these stuff are done locally, and this is what we were concentrated last 3 days here in Daejeon, and we did it. So now we have time domain data, and we can push them in the cloud storage. So as I said, since we do continuous measurement of ice signals, we usually name our files with a timestamp like year, month, day, and so on. So we know when the ice was done. This is not mandatory. You can change it in any way you want, but it should have some kind of increasing labeling, and we should somehow know how to reference which ice comes from where. But I'm not, so now I was talking up until now only regarding the measurement. I wasn't talking about the ice curves. So how we do it, we do it in different ways, but most commonly, when the time domain data are measured, they're uploaded to some storage device for permanent storage, because we can think of some other analysis later on so that we can access the data. Then we actually calculate the ice curves in the cloud. And then we calculate everything using the algorithms that I showed yesterday and the day before yesterday. And then this ice is pushed back into the cloud so that the researchers can download them and do whatever they want with it. What we are going to do here is something additional. Instead of calculating everything in the ice, I'm going to, as I already gave, I'm going to prepare now a small script so that all this analysis can be done locally in Korea. So you don't have to worry about sending the data somewhere, do whatever it is. Everything will be done locally. So besides calculating the ice, there will be tools that immediately check chronic conditions. And as I already gave you examples, you can then use the ice to calculate TRTs, to do a frequency analysis, and then you use your expertise to do fault detection and so on. I was talking yesterday about file sizes. So I'm going to jump these 3 slides and concentrate on file sizes and why this is a problematic thing that should be taken care of. So in Daejeon, we are using quite an efficient storage format. It generates approximately 25 megabytes of data per ICE. In some cases where we have bigger stacks, this can go up to 500 megabytes, so half a gigabyte per measurement session. And if the experiment runs for a couple of years, maybe these can pile up to several terabytes, as I already told. It's not a problem in the cloud storage, but over and over, it just adds up. And by using a simple trick, we can actually reduce this load quite a lot. So what we have here is, in Daejeon, we have these filters that I was talking about. They're not drawn here. They're on top of these lines that filter the signal to 10 kilohertz. This means that we have to sample every signal with 20 kilohertz sampling frequency. And for the lowest frequencies, we have to acquire approximately 190 seconds. This adds up quite a lot. And because in the low frequency range, we do not need that much high frequency sampling, before uploading to the cloud, we can easily decimate this signal, which means that instead of storing all data points, we store only a reduced number of it. Why is this possible? Let me show you with an example. Let us assume that we want to acquire this signal here. So we sample it really, really fast. So all these dots here are points where we sample it. And it's okay, we see that the signal is nicely represented, but what we can do is we can actually reduce the number of points as long as we do not break this Nyquist-Shannon theorem all the way down to twice of the maximal frequency that we would like to use. So this one was sampled with 1 kilohertz. This one was sampled with 500 hertz, already twice less amount of points. We can go even further because the signal is not that fast. We can sample it, we can downsample it to 200 hertz, to 100 hertz. And although one would say, well, look, this signal looks really nice, this signal looks really dodgy, from an information perspective, both of these signals contain exactly the same combination of data. So this signal takes 1/10 of a storage in bytes than the first one without losing any information. So that is why we usually decimate the signals before storing them. In such a way, we can decrease the amount of bytes that we are moving around. But we have to be really careful. This doesn't mean that if we sample this signal this often, and if we want to take only every 10th point, that we just take the original signal and take every 10th point. We have to first filter it out because the signal might have some high frequencies. So we first filter it out, and then we take every 10th point. This is something that you don't have to worry about that much because there are a lot of tools that does this for us. But if we do not do this properly, then this might happen. So we have this original signal here. We didn't filter it. We just took every 10th point. What happened is something that is called aliasing. And now the signal became this. So there are like wiggles, and there are two frequencies, the original one and one that is called ghost frequency. This frequency was not present in the original signal, but appeared now because we didn't do filter and decimate. We just made decimate process. So these are simple, really simple signal processing tricks that we are going to use in the post-processing part after we make experiments here in Dijon in order to reduce the file sizes while in the same time not losing any information or making such simple mistakes. Okay, so now the final stage is we have an experiment, we do a data acquisition, we obtain the time domain data. Currently in Dijon, we are at this point. And we did this cloud storage because we are still in the prototyping phase. We don't want to add any extra additional step until we realize that all the pipelines are working correctly. So in the course of the next weeks or months, we will add this trick here that will take only every n samples, and this will dramatically reduce the file sizes while not compromising the quality of the data. This will make the processing faster, storage of the files easier, everything will become much easier. And this is something that we are going to add, I guess, sometime in September. It is a software module that the guys here will program in LabVIEW. That will be it, a simple procedure. This decimate stuff in LabVIEW is already built in, and they don't have to worry about it. But at the time moment, we are ignoring this part. We know that we are storing over big files. We said, okay, let's forget about this. Let's just test whether everything works. Then we will start the optimization process. So this is the final thing, how the processing pipeline usually looks. So we have an experiment, regardless whether it's fuel cell, electrolysis, batteries, whatever experiment you have. You do the data acquisition, you take the time domain data, you decimate the time domain data, so reduce its size without compromising the results, and then you store it somewhere. You don't, for security reasons, you should not keep it on a single PC at the laboratory because the PC can be broken, stolen, whatever. We should have the data stored somewhere safe. So we usually suggest to have some kind of permanent storage. This can be on-premise cloud, whatever your institution has, you can use it. And then when you do all of this, this means that the data is now safely stored. Then we can take time and calculate ice, do whatever analysis, and so on and so on. This doesn't mean that if I draw like a time axis here, this doesn't mean that after storage and calculating ice, there will be months. This can be like delta t 20 seconds, because you have to wait for stuff to be uploaded, and then we can calculate ice immediately. Or we can just pile up the data and do post-processing later. For example, the things that we calculate, that the guys here in the Dijon lab acquired just during the first lectures, they've uploaded it to my cloud storage in Slovenia. I'm going to calculate the ice curves and check the data while I will be on the train to Guangzhou today. And then I'm going to give them all the data plus everything that I did. So the delta t here will be maybe 5 hours. But from tomorrow, they're going to do this by their own here, and delta t is going to be maybe a couple of minutes. And as they become more and more fluent in all these files running around, this time will shrink, shrink, shrink over and over. And if we then realize, oh, look, there is an additional trick that maybe we can do, improve the data or stuff like that, because all the data is stored here on the cloud, we can take all the historical data and reprocess them later on. I don't know, 2 months from now, 1 year from now, we think of some other modeling technique, we can come back and reprocess everything. So that is permanently stored for, in quotation marks, for eternity. We can do whatever we want. So this is the pipeline that we are using for performing our experiments when we do it in Europe. This is something that I now push the guys to follow, at least during the prototype phase. And after this is done, then you can change this pipeline in a way that suits you the most, based on the security guidelines of your institution, based on your hardware installations, whatever your local peculiarities are, you can do it in your appropriate way. What I wanted to say in a very, very long way is that you don't need to hurry to calculate ice immediately after you measure the data. It should be done as quick as possible in order to be able to detect changes, but there is no pressure to do it. The data will be stored, they will not be lost, so you can take some time if you have something else to do in the meanwhile. So this flexibility, this gives us a lot of flexibility. So final, as I said this morning, I don't think that I will use this second half of the lecture in full. The last part will be how are we controlling these instruments through a PC. So we are running experiments 24/7. This means that there will, in many cases, ice measurement and ice calculations are performed without any human intervention. So the PC that is controlling the experiment must be capable of triggering ice curve, ice measurement by itself, handling the power supply, handling the electronic load. So it has to somehow communicate through a machine-to-machine interface without any human intervention. So luckily for us, this is not our invention. Luckily for us, all instrumentation that are modern enough, modern from 95 onwards, I think it was like this. It's an IEEE protocol called Standard Commands for Programmable Instrument, SCPI. It has nothing to do with Python, although it seems it has a reek of it. This is the abbreviation. The protocol is really, really, really simple. So you can, I have for every instrument that I'm using, I have Python code that can control it. But as here we are not using Python, you can do it really simple in LabVIEW, and the guys here have already done it with their instruments. The protocol is really, really simple. It is a text-based protocol, and it defines a syntax that is common regardless of the instrument, regardless of the manufacturer. So if once you get a hold of it, how this works, you can use it to control almost all smart instrumentation wherever you are. So what's the style? The style is, wait, I'm going to jump and then I come back. The style is like section 1, column, section 2, column, and so on to infinity. What does this section mean? Well, imagine if you're at an instrument and you would like to change a voltage. How do you change it? Well, there are buttons on the instrument, and then you have to click, for example, measure. Then there will be a menu that will say voltage, and then will be a menu to ask you, is it a DC or AC? And you will click DC. It is the same thing. So you tell the instrument, I would like to measure column, voltage, column, DC. And if you put a question mark, it says to the instrument, please measure this. Or you can say DC and put a number here, 5. This will tell to the instrument, position yourself at 5 volts. And this kind of structure, this kind of strings, is valid for every instrument that you have. And that is how you actually control your instrument here, your power supply. That's how the guys in Dijon control it. Our excitation unit, on the other hand, I'm going to jump here a lot. Our excitation unit, then I come back, is controlled in a different manner. We have a GUI where a person can click, but this is not the way how we would like to do it. That is why we have prepared a web-based interface that has now become even more common than that protocol that I was saying. And performing ice measurement with our device is extremely, extremely simple. So you call a command prepare. Sorry, what I did, cancelled everything. So you call a command prepare, and then you actually ask what kind of experiment are you going to do. I'm going to come back to that. Then you ask it, is everything prepared? Then you just say trigger, and ice excitation goes. From this point to this point, this duration is less than 1 second. So you do it like and ice immediately starts to be generated. The excitation for yes. What is this experiment ID? So this experiment ID is exactly the thing what I was talking about yesterday. So we have pre-programmed at our device several DRBS signals with different bandwidths, and this is because of this time duration trick that I was telling you about. And each of these DRBS signals have different duration. This is duration in time, and different lowest frequency. I don't know where this 25 came from. It should be 0.01. What we found out during our work in fuel cells, in electrolysis, solid oxide electrolysis in particular, is that this lowest frequency can somehow be influenced by steam generators or whatever it is. So we are not using this signal. Instead of 10 seconds here, we are using 194 seconds. And because, oh Jesus, I don't know what I'm clicking. And because, so we are not using this, we have here 194. And because of this duration, this is now 0.02 hertz lowest frequencies. So guys here are doing these experiments. This one, this one, this one, this one, and that. So 1, 2, 3, 4, 5 excitation signals. All together, they will be like 195, 196.5 seconds. This is how much time we are going to use to perform one ice measurement, and we will have the data from 0.02 hertz up to 10 kilohertz. 10 kilohertz. And we will be able to select the frequency bands afterwards. So we just do the measurement, we have all the data, and then we can play around with it in the post-processing part, wherever we think of. So now if I go a little bit back, since we can control the instrument in such a way, programmatically, we can actually pre-program different scenarios how we are doing ice. Usually, what is happening is you make an IV curve measurement at some point, you stop here and you fix this DC point at some current level. Here is, I don't know, 45 or whatever, and then you do ice measurements here over and over again. But this doesn't have to be a case. What we can do is, let me find, yeah, here is a better place. What we can do is, and what we are actually doing in some places, so this is time, and this is DC current in amps. So we go up, make the first IV curve up until some point. Then we do some flat line, and here maybe we calculate several ice measurements, and then we go to different, play around and explore how this system behaves at different set points. And this can be done automatically. So we can pre-program such a load profile and just hit play, and the instrument will go and do measurements at these points, and then at time t1 it will jump to a different DC level. At time t2 it will jump to a lower level, and will do all these things accordingly. Yes, you might argue changing set point this much might require changes in the fuel, in the flows and stuff like that. Yes, but if we have access to the controller that is controlling the experiment, we can perform such complicated experiments without any human intervention. That is how we are doing automatic reversible SOAC operation in Graz continuously for such a long time. So in a nutshell, what I wanted to, and I won't bother you anymore, so I'm going to cut 45 minutes of your time because I really don't have anything extra to tell you about how are we doing experiments and how are we doing it in Dijon. What I would like you to take away from everything that I was saying today is that you do not need very, very expensive equipment to do ice measurements. Oh yes, sorry, we did. Thank you. Thank you very much. I will change it. So you don't need very expensive components to do ice. You can, as I showed you, you can use really not cheap, but I would say cost efficient off-the-shelf products. If you have simple, it doesn't have to be Python, simple programming skills, you will be able to control everything. You can control, when you are buying instruments, check that they support this protocol. Almost every modern instrument supports this, but double check. Everything that I use here to do ice is open source. That means that either it's written by me and I give it for free, but majority of the stuff are publicly available tools that have no licenses. You can use it even for commercial applications. There are no strings attached. And at the end, this means that it gives you a very, very easy way to customize your experiments. So this is everything what I had for today. I'm not going through the Python script that I had it on the slides. Everything is commented on the repo. So if you have any questions,